Look, if we look at this graph, at the set S here is region, triangular region, so it is a convex set. But the graph of the function, so let's make it bigger here. If you look at the graph of this function, it's not convex. You see, it's yes, we cannot say it is convex, because if you take point here and here the line segment, so the function yes remains, but if you change, maybe it is convex, we will see. Okay, but for the function of one variable here, globally it is defined everywhere, and it changes convexity. Here it is convex, here concave, and then convex. So globally it's not, we cannot say it's always convex or always concave, but still it has a global minimum. So there are results so that allow us to conclude about global extreme point without requiring the convexity or concavity of the function. So it uses what we call the extreme value theorem. So here it is, extreme value theorem. So let's use the following abbreviation. Sorry, theorem, extreme value theorem. Okay. In calculus, we know an extreme value theorem that says if you have a function that is continuous on closed bounded domain, then it has a maximum and a minimum. So it's a similar one. It's not just we need to work on sets not in one dimension. So we bounded, still we keep it bounded, and closed also, closeness that we defined for sets in Rn. So here is the theorem. So the theorem says if you have f continuous, or yes, we have it here. I don't need to write it. So the main theorem is this one. So let's move it here and make it bigger. Okay. So here is my theorem. And to make it bigger, larger, so that you can see it better. So the theorem says, the extreme value theorem says, we need just we don't need convexity necessarily on the domain we are working on. We need but we need it to be closed and bounded. Okay. Closed, we said a set that contains its boundary points. Bounded, the size, it's not infinite. The point is bounded, any point, the norm of the point is bounded by a constant. And we need for our function that it to be just continuous, which is weaker condition than C2 differentiability, we see. Then F attains, the theorem says attains for sure its maximum and minimum value on S somewhere. That is, maximum exists, okay? And it is on S, in S, that means there exists a point somewhere in S where the maximum is attained and the minimum is attained. So that's why so a method, this suggests a method of search. So let's describe it, the method of search. Method to find there's maximum and minimum. First we look at find the interior critical points. Okay. Then find the extreme values, so the maximum of f on the boundary and minimum of f on the boundary. Okay. Then compare. We know that because our set, we don't know, here is my set S. Okay, so either I am here at the boundary either I am inside the interior here. Okay, so here I will look for f prime x equals 0. Yes, and here on NDS I will look for the maximum of f on ds and the mean upon ds. Then you compare. We use comparison. Then compare the values. Compare the values of f. Values of f. So you can, usually I prefer to put a table like that and gather all the, for example, the critical points. So here critical points, that means where either you have f prime x, remember, equals 0, or f not differentiable, okay, where or f not differentiable at x. So you gather all the points here, you compute the values of f at these points, and you look at maximum values, so the points at the boundary, okay, um, the points at the boundary, and take their values, points at the boundaries d to s, and you take the value. Then the maximum will be among these maximums and minimum of these values. So this is a way how to compute, to look for. So let's do a first example. Yes, the first example is the following. So first example is the following. Here is an example. So it is about this one. So let's make bigger the, okay, here is my function. So here is my formula, and I am interested in finding the max and minimum. So this is my function. Yes, fxy. So it's minus x2 plus 4xy minus 6x minus y2. Okay, so the question is, this is my set S, okay, and I need to find mean and max, mean of f on S and max of f on S. How to proceed? Okay, so here I am in the situation, yes, S is closed and bounded, plus f is C0 on this set and everywhere. So by the extreme value theorem, f attains its extreme values. So we want to know what are these values, and they are reached on which at which points. Okay, so let's proceed, follow the scheme we express it here, we describe it here. First we will look for the interior critical points. Okay, so first step, interior critical points. So here I don't have points where f is not differentiable. My function is differentiable everywhere. Interior critical point. So they are solution of gradient of f equals 0. Okay, what is gradient of f? The partial derivative with respect of x minus 2x plus 4y minus 6. A partial derivative with respect of y, it's 4x minus 2y. So we want to solve the equation, the system 0, 0. So it's the same to say that I have y here. From the second equation we will have y equal to x. The first one minus 2, let's simplify by 2, so it will be minus x plus 2y minus 3 equals 0. So by substitution, if you substitute, you will get here minus x plus 4x and minus 3 equals 0, which gives me x equal 1. Okay, and then substitute y will be 2. So we have the only point 1, 2. Is 1, 2 inside? So let's here's describe well my set S. So S, my set S, here it is S. Sorry. So this line L1, L1 here. So L1 here is just what is described by the set of points that are x 0, okay, with x between 1 and 2. L2, L2 is the set of points. So let's make my graphing bigger. Okay. Okay, let's like that, it's much bigger. Okay, now L2 will be the set of points x, so x is fixed, is 2, so it will be 2 and y. Okay, y is taking values from 2 to 6, y from 2 to 6, and here the point, the end point here is the point 2, 6, and this is the origin 0, 0. So L3 is a line that passes from the at the origin. Okay, so its equation here is 3x. So L3 is the set of points x3x. Check 0, 0, x equal to y equal 6. So yes, it is my line, and x takes the value from 0 to 2. You see, so now I see my set completely. Great. Yes, now what we wanted to check if whether 1, 2, the point we found, 1 and 2, is it on the line 1, 2? So it's not on the line because 1 should be at 3. 1 is at 3 for that is on the line. Okay, so 1, 2, the point 1, 2 is the only point, critical point. Okay, it's an interior critical point. Okay, so we have one critical point. 1, 2 is critical point. Okay, great. So yes, I check it, then I will keep one critical point. One critical point, interior critical point, okay, belonging to S0. This is the point 1, 2, and we have the value f at 1, 2. So if you substitute, you get the value minus 3. Great. Now, okay, now let's continue. We found yes, the one only critical point. Now the second step is to look what is happening at the boundary. So we want to look at the maximum values taken by f at the boundary of the S. Okay, so let's start on L1, then L2, then L3, and then conclude. Okay, so this is how we proceed. Yes, when we have closed bounded domain. Of course, here the shape of the domain is important if it is complicated. So maybe the method is not useful, even we are sure about the existence and the existence of the maximum minimum, but it's hard to find them also. Okay, so each time you have to, depending on the problem, you have to decide which method is practical or okay. So let's do, then we said let's continue and look for now look for the interior on L1, for example. On L1, so we have f x0. If you compute, substitute y equals 0, so you will have minus x2 minus 6x. So you have a function, let's call it g of x, that is a function of one variable and x between 0 and 2. So it's easy, let's derive g prime. So if I compute g prime of x is minus 2x minus 6. Okay, and my x takes the value from 0 to 2. So g prime is 0 only for x equal minus 3. So it will be positive. So let's deduce minus 2x minus 6 is positive if and only if minus 2x is greater than 6, equivalent to x less than minus 3. So since I am from working for x um, between 0 and 2, it's greater than minus 3, so this quantity is always negative here, and my function then is decreasing, my g of x, okay, is decreasing. At 0 it takes the value 0, at 2 it takes minus 4 minus 12, which is minus 16. Okay, so I can read here the maxima. I have continuous function on closed bounded, so I have the maximum and minimum, the same reasoning, but since we have a function of one variable, we can make this discussion on table like that, okay, and see that the minimum is at 0, 0, so I can start gathering the points on the table. Okay, so let's put our table, so xy and fxy. So I found the critical points 1, 2. Let's put it here 1, 2, and the value taken is minus 3. Now we found now 0, 0, and the value taken will be 0 by f. Okay, the other point is no 0, sorry, x equals 0 and y, yes, y is 0, and this time now x equals 2 and the y is 0. I am on the line L1, okay, so 2 and 0, and the value taken, say it's minus 16. Okay, so now we gather them, just it's enough to have to gather them. So let's do the same work now on this time on L2, on L2. So f takes the values at 2y. So if you substitute, you will get the expression. So f2y, we have the expression minus y squared, okay, plus 8y and minus 16. Let's call this function h of y. So again, a function of one variable with y between taking values from 0. So let's put y taking values from 0 up to 6. The derivative h prime of y is minus 2y plus 8. So let's discuss the sign. Plus 8 is positive, will be if and only minus 2y is greater than minus 8, if and only fy is less than 4. Less than 4, so I have 4 here. Okay, so 4 is inside, so that means it will be positive if I am here, and for values greater than, it's equals 0 here and negative here. So my function does something like that, increase and decrease this quantity. Okay, at 0, so we will have minus 16. At 4, we will have the value 0 if you compute it, and at 6 we have minus 4. So let's gather again these values. So we'll have this, yes, I can consider them all, or just this one is already here, 0. For y equals 0, we had the value minus 16, and it is the point 20. Let's we have the point 24, okay, where f takes its maximum L2, and the point, the other point is the point 26, where f takes the minimum value. No, the minimum value is this one, not this one. So we can avoid considering this point. Okay. So we can not consider. Yes, we can avoid to include this one because we want just the maximum minimum values. This is one, the minimum, you see. So this one is the min on L2, and this is the max on L2. Here the min on L1, and this is the max on L1, okay, of f, of course, of our function f. So yes, and we said the value taken is 0 here. Okay, great. And the last set is what is happening. We want to explore what is happening on L3. So on L3, let's continue doing it here. On L3, let's do it here. On L3, so my function, I will work on the line L3, and the expression is 2x2 minus 6x. This is, let's call it Lx. Okay, same thing, small table, x belongs here from 0 to 2. L prime of x is 4x minus 6. So we have the value 3 over 2 that is appearing. Positive here, negative here, 0 here. So my function L decreasing, increasing. Okay, at 2 it takes the value minus 4. At 3 over 2 it takes minus 9 over 2. And at 0 it takes the value 0. So here clearly this point is important, this value, and the maximum value at 0. 0, it's a 0, 0. It's already here. We don't have to write it again. So the only point we need to add is the point 3 over 2 minus, 3 over 2, 3 times 3, that is 9 over 2. Okay, and the value taken is minus 9 over 2. Okay, and from here now we gathered all the maximum extreme values at the boundary and the interior critical point, and the values of f at these important points is gathered on the table. Now we just compare and conclude. We see that this is the smallest, the minimum of f over the s will be over our set S, and the maximum largest value is 0. Okay, it is attained at 2 points at 0, 0 and 2, 4. Okay, so this is the maximum of f on S, and this is also the maximum of f on S. Okay, so and if you you look at your graph now, so this is how you can solve your problem. So if we make, let's put bigger, magnify. So we see that at 2, 0, we have the minimum value, the smallest value, and the largest is attained at 0, 0, and 0, 0, and 2, 4. So 2 and 4, 2, 4. Okay, so those are, yes, the value 0 is the maximum value. Okay, so yes, so this is but without of course we cannot graph each time our surface and check. Okay, so theoretically the theorem says for sure this maximum minimum are attained, and we have a procedure that we can apply, and it is feasible, yeah, the calculation, when the calculation are feasible, so we can have answer to the problem. Okay, there is another theorem that it's also an extreme value theorem, but this time not on bounded sets, it's on unbounded sets. Okay, unbounded, and we need also just continuity of our function. Okay, here it is. The theorem says f continuous on unbounded set Rn, and we need behavior of at infinity of our function. It's both side, yes, with a norm of x large enough, it's plus infinity, then for sure you have minimum is attained somewhere on your set without requiring convexity of the domain or convexity of the function, you see, or regularity more than continuity, which is a strong result. Okay, so an example for that, so it is illustrated here on this graphing. So here it is. So hey, so this is our example. So let's discuss this example. Apply this. Okay. So we said we don't have convexity. We don't have our domain is not bounded closed. So we cannot use the other previous theorem. This is unbounded. We don't have convexity. We cannot use the argument of convexity, but still we have a global minimum. So here we will look. So the limit behavior, yes, limit here of my function, which is 3x4 plus 4x3 minus 12x2 plus 2 as absolute value. That is absolute value going like that. That is, I'm considering. So for polynomial, usually how we do, we take the highest term, that is the term that is dominating the behavior of our function. So we will have something like that. We can write something like that so that we justify why we have this. And having this writing means I'm considering to both behavior, plus infinity or minus infinity. And you see each of these terms will approach, each of them will approach 0. This one will approach 0. Okay, this term will approach, this one also will approach 0. So finally the behavior is the same, that behavior of 3x4, which gives me yes plus infinity. So from the theorem, from f is continuous, here this is my function f. Okay, f is C0 in R everywhere. Okay, so and I have this behavior. So from theorem 2 there exists, so from theorem 2 there exists x star in R such that, okay, such that the minimum of f over R is f at x star. It is attained somewhere, the minimum. Okay, now since my function, now I know that it is a regular function, I can derive it, and my R is, so now identify, let's identify x star. We would like to identify it for this situation, otherwise for its existence we have the theorem that ensures us. So let's proceed for, so the set S is open, and f is regular, is C infinity. Okay, so so x star is also solution of, is critical point of solution of f prime of x equals 0. Okay, so let's solve then the equation f prime of x equal, so the derivative is 12x3 plus 12x2 plus 24x. If we factor this expression, we get the following. It is x plus 2 times x minus 1. Okay, so we have 3 critical points. So equals 0 if and only if you have x either 0, minus 2, or 1. Okay, now which one? So since we have the minimum is attained, it is a critical point, then the minimum of f over R is will be the minimum of this among these values, f0, f minus 2, or f1. Okay, over among these values. Okay, and if you compare, that is, if you compute these values, they are f0 is 2, the other one is minus 30 and minus 3. And exactly, yes, the value is minus 30. That is, the minimum is at minus 2. Okay, and yes, you can see it here. we can see it. Okay, we can by graphing we can check that it is. Okay, the theorem doesn't say there is a unique element. It says just that there exists at least one. We have point. Okay. Also, this situation also illustrates when you have critical points, that doesn't mean that they are maximum point necessarily or minimum point, because here we found -2 is minimum points, but 0 and 1 are not maximum or minimum. They are local maximum, local minimum. We can check. Okay, but here for the global, our interest is about the global optimal point. And if you look at your function, it doesn't have global maximum. Okay, remark here, let's put it as a remark. So remark, we have limit of fx as x approaches plus infinity is plus infinity. So f maximum of f do not exist globally over R. Okay. Okay. So yes, we have an answer about the maximum. Global maximum doesn't exist, but still we have a local maximum that it exists. Okay, so this is so those are, you have two other theorems that answer some questions about global extreme points. For one, for closed bounded sets with continuous function, and the other one unbounded set with infinite behavior for and continuous only functions.